So let me get started for today's lecture and let me review where we were before the midterm exam. The first one that I want to recap or review, that is convolutional autoencoder, and next topic is, of course, is FCN, fully convolutional neural net. I think these two topics is not have not been in the midterm exam. So the autoencoder is a nonlinear version of dimension reductions. I think like in machine learning, the similar thing was principal component analysis. And here is the concept of autoencoders. I suppose that you all know and familiar with that. One thing that I want to mention is that, like, let me see, you guys know what kind of convolutional operating is how those convolutions works but in the opposite, usually convolutions and the max pooling is kind of to the downsamplings. But what we want to do for the convolutional autoencoders, how we make convolutions in order to make upsamplings. That was the motivation that we have. So in TF or Keras, we have convolutional 2D transpose. So actually, I didn't explain why they have transpose in the name, but you don't need to. Probably, if you want, for the advanced learners or students, you can Google it, and easily you guys can find the documentations to explain what's the meaning of transpose and why they have transpose in their name. And that's what did that. So this is kind of typical structure of CAE, convolutional autoencoder, like that. And of course, in this part is latent space, just like we discussed it in the autoencoder. So dimension reductions with a smaller dimension of that, we call it latent space. And that's what the reconstructing images, and that's probably all things that you need to know. And let's move on to the next one. Is that it's a FCN, the fully convolutional neural net. So basically, we start talking about segmentations. Okay, autoencoder is unsupervised learning for dimension reductions, and FCN is motivated by we want to do segmentation task in computer vision things. So what is segmentations? I don't need, probably the pictures probably tell everything. So suppose you have an input image, the corresponding output image is like segmented. So these pixels like belong to dogs and cats and background, things like that. So we need these paired images. Okay, and I guess here for the segmentation is different from classifications, in a sense that we need, let me see, classification is what's in the image, in the input image, and plus for segmentations we need to know where. So we need to know location of pixels, each pixels. Okay, so since we already did the FCN and segmentations, that's why we need skip connections. So that's the kind of the purpose that we had. Let me see. This is FCN. No, just for I will say of the segmentations. In order to memorize or get some kind of location information from like these upstream layers. So from CAE to FCN, so we can do segmentation task. And these are kind of the detailed explanation for the what's the skip connections. And the origin from the skip connection is actually built up to they developed skip connections for the ResNet, right? Residual learnings, but we can use that thing for segmentation task as well. So let me see. This is the basic architecture of ResNet. And the original purpose is that since you have the deep layers, you know that is a lot of gradient vanishing behavior effect, things like that. So if we have skip connections, probably we can overcome the issues, the gradient vanishing effect. So that was the original purpose of having the skip connections in the ResNet. But again, like I said, we can use that the same concept or same structures for fully convolution networks for segmentations. And the example that I hear, this one is that in the material image, and these are the typical material images we have. And if we have two different phases here, we can do this kind of segmentations. This one is, you don't need, actually, in the previous version of TensorFlow, we had the one-hot encodings. That's why we have, even though it's a binary classifications, we need two pictures. But now in Keras, we don't need to do it. So again, the example that we have here is because we learned the transfer learnings, so we want to make use of that transfer learning techniques here as well. So we fixed it from the VGG16s, and the downstreams, so we set it as trainable. So we can reduce the number of parameters that we need to, or to estimate it. So that's kind of the result here. So input and segmented output, and we overlapped it. So it's kind of okay. So I mean, like I said, all of the examples here is like, don't worry about the accuracy or performance too much, because I just wanted to show how to program it, like basic structure of what's the concept of that ideas. So probably you can, if you want to increase the performance of the like accuracy, probably you can do more, right? I think that was what we learned before the midterm exams. And let's move on to, or continue on to the next topic. Okay, super resolutions and deblurrings. I mean, this is going to be another example or demonstrations related to FCN. Before that, let's talk about image restorations. In digital images, suppose we have some corrupted images, and somehow it could be like arise during image acquisitions or image transmissions, whatever. So you don't need to worry about the how, but say somehow we do have some corrupted images. A lot of reasons, like imaging sensor can be affected by like ambient conditions, or inference can be added during like inference, or noises can be added to the images during transmissions, whatever. And the input, or the only thing that we have is corrupted images. We don't have the ground truth. So a lot of like folks or researchers in the computer vision is that we want to reconstruct or restore the like from the from the corrupted images. So to recover the original image from degraded one, so we want to recover the original image from degraded ones. The thing is, with the prior knowledge of the degradation process. Okay? Without these, I mean, if someone claim that approach to use, they claim that I'm able to reconstruct or recover the original image from degraded one. And if say that that's kind of fake, but here is some constraint. We wanna do this kind of image restorations with prior knowledge. So that's how can we learn the prior knowledge from? The answer is from the data. Okay, from the data we can gain prior knowledge. Using that gained knowledge, we want to do image restoration. That's kind of the story that I want to do. So suppose we have some kind of noise or whatever is corrupted or degraded one, and we want to recover it to the original one. And here is image restoration is that it's a part of inverse problem. It's part of the inverse problem. Okay. Then the question is, what is inverse problem? It involves the modeling of degradations and applying the inverse process in order to recover the original image from the inadequate observations. Right? That's the inverse problem. The observations contain incomplete information about the target parameters or data due to physical limitation of the measured device. I mean, just basically it's degraded or corrupted or noise added, whatever. So observation contains incomplete informations. But thing is that we want to do is starting from incomplete informations or images or data, whatever, we want to recover it with a prior knowledge that we want to learn from other data set. Okay. And another thing that you have to remember is that the inverse problem is not unique. It's not one-to-one problem. So that's why it's a challenging and difficult problems. It's not unique. It's not one-to-one. It's one-to-many problems. It's ill-posed. So it's not like cannot be determined uniquely. That's the issues that we have. In general, I'm talking about like a general statement for inverse problems. Let's see this one. Suppose we have the original image. Then we can do a lot of things in order to make corrupted or degraded one. We can add noise. We can give some kind of blurring effect, or we do downsamplings. That's something that we can do. The output of that probably the observed images, which is corrupted one or degraded ones. That's something that we can do. Okay. From the observed image, it's a denoise. No, we want to do inverse problem. We want to solve the inverse problems with this observed image as input, and we wanted to restore or reconstruct it. Okay, so starting from the original one, we can make corrupted one, and we hope that we are able to reconstruct right? And here's two things that I want to address at this point. And suppose we know that. Suppose we know, okay, so we add some kind of noise or Gaussian noise or salt and pepper noise, whatever. Or suppose we did this kind of blurring effect, we add that, or we add some like 2x2 downsamplings, whatever. If we know that, we can just do reverse it, right? Then we can reconstruct it. But in a practical sense, the issue is that we don't know what kind of, that's the problem. We have no idea. Right? So the only thing is, okay, so in the real life, in the real world, we're gonna start from this one. The only thing is we have observed the image, which is corrupted. That's the starting point. Right? These, we have no idea. You have no idea. And starting from the observed image, how can we reconstruct or restore the images? That's the inverse problem. That's the inverse problem. So I mean, this is not easy, right? In conventional way, it's almost it's impossible to solve. I mean, in general, that's a true statement. That's a true statement. So the idea is that here is that since we kind of I'm trying to show a lot of data-driven method. Okay, so one of the example in this because we learned FCN for segmentation task. It's basically it's image to image translations, right? Think about it. Convolutional autoencoder and FCN, the input and output. The thing is, both of them are images, right? So we do some kind of translations. Things from image to image, right? So let's see. There are many examples related to inverse problems in a computer vision, and one of them is a super resolution problem. We call it SR. Suppose we have, how do I say, if you think that is as a MNIST data set, it's a 28 by 28. It's a small picture of it. And somehow say that the 28 by 20 is the resolution of that image is not good enough in some sense. So I want to have like or like 100 by 100, whatever, maybe 1000 by 1000. So somehow the image that I have is raw resolutions, but somehow I want to have high resolutions. We call it this super resolution process. If we have 28 by 20 like in this data set and build up or do super resolution, it's impossible. It's impossible. Maybe way that we can do is that like we can do linear interpolations. That's one thing that we can do. But I'm not sure whether let's say we have now this is 2D example that we have. And let's see, think about 1D example I have. These are the resolutions in like X. Suppose we have these, the Y values. And let me ask, we don't know what here. We don't know. We have no idea. And we have no idea what kind of application system that we have. Only thing is that we have only these discrete dy values. That's measured. And what do you think will be the proper, how do I say, kind of okay estimation of that? Any ideas from data set that you have? What about these data points? There are many ways that we can do. Probably I will just take the values from previous one. That's okay. Or like take from like this. I mean that could be, or probably better way that we can do is like linear interpolations, probably. That's kind of the assumption that we made. Has nothing to do with data or has nothing to do with physics that we have. We have data points, sparse data points. I want to make up in the what kind. I want to estimate the values in the middle. Linear interpolation is one of the, and I think most frequently used. Or someone says I don't like linear interpolations. Probably, like say we have, like we do, like how do I say, polynomial fittings, like that. We can do, and I will say this. Someone's gonna claim that this method is better than just linear interpolations, whatever. There are many ways that we can fill out the blank. We call it super resolutions. Okay. And these the assumptions that I made. Like take the data value from the value from previous or the one after, or take linear interpolations, or use some polynomial data fittings. That those like thing is we can say it's prior knowledge. We can say it's assumptions or prior knowledge that we have. We don't know which one is good, but if that's linear interpolations, that means I believe that, suppose this linear interpolation is the best, then means I believe that the prior knowledge that we have from this data set or the system that where the measure such kind of data set is linear systems. That's kind of my belief. Those are kind of the conventional way or traditional way of looking at super resolutions or looking at how to fill out the blank. Right. And another perspective or philosophy from data-driven or deep learning model is that, hey, I'm not going to ask users to provide like prior knowledge. I want to learn such prior knowledge from the data set. So ignored all these kind of things. What we can do, suppose we have high resolution image. I mean, in order to have data-driven super resolution method, we should have high resolution first, right? That's a constraint. That's given. And we can do downsamplings. That's image processing. You can think of it as a max pooling. Right? We're gonna do downsamplings. Then we can get, or sometimes we can add noise. is in order to make your method is more robust, like noise robust, we can add that. Then we will get low resolutions. So this is given. This is the output of blurrings or downsamplings, whatever. Now, surprisingly, now you do have. Now I wanna learn prior knowledge from the data set. Okay. Now I wanna build up the deep learning networks. In that case, what's the input? What's the input for the deep learning models? What's gonna be the input? Gonna be the input, and this will be the output. I'm gonna show a lot of different pairs of starting from low resolutions to high resolutions to deep learning models. You see what I mean? So in real world, so this one was the input, and I'm gonna do some manipulations in order to make the output low resolutions. I can do downsamplings, or I can add noise, whatever you can do. It's image processing, has nothing to do with data. For deep learning perspective, I want to teach the prior knowledge starting from low resolutions to high resolutions. So this will be the input, and we have deep learning models, and this is going to be output. Basically, we're hoping that the deep learning model is able to catch prior knowledge of that. You see what I'm trying to do? Okay? So by looking at it, the input and the output type is images. So this one is same as image to image translations. So then, we can use FCN. And of course, we want to keep all the locational pixels, so probably skip connection is going to help us a lot to get the location informations from upstreams to downstreams. That's the kind of the basic philosophy or basic ideas behind super resolutions. Right. Of course, this one is the kind of the simplest baselines models, and if you Google it, like search super resolutions approach, you're gonna have, like, I would say, tons of different networks. So let's move on to one of the examples that are here. Again, I come with material images. As you can see here, it's the size of the image. I make the same size, but if you look at the size of the pixels, this is low and this is high, right? And if you keep the pixel size equal, probably this one is like the image size is much smaller than what you are looking at, right? So again, the first step is that somehow I need to gather high resolutions material images, a lot of images. Now I can do down sampling image processing to get low resolutions. Now the low resolution image gonna become the input to the the FCN networks, and this one is going to be the output. So let's build up another FCN models. This is, again, the architecture is not the optimized one. I'm just showing one of the possible way. So don't worry about whether this one is this. Don't worry about the performance of or accuracy, whatever. So first thing first, looking at the size of the input and output images, I want to do super resolutions, so it's much smaller. The input image is much smaller than output. Right? Now, starting from, so in somehow we need upsamplings, because starting from the smaller one, we have to increase it. So at some point inside the networks, we need to convolution to the transpose somehow, so that we have, and we do have skip connections as well. Now, I don't think I need to explain what's the purpose of having skip connections in this model anymore. That's the structure that I'm going to use and demonstrate for super resolution example here. I mean, you can do like auto-encoder structures, but in this case, I didn't just kept the same size, and from maybe in one of the downstreams, I do upsamplings. I don't know which one is the better, but I'm pretty sure that you guys can change the size of the images in the size of the image in the middle layers. So let's suppose, I guess that's the size of the input. And let's see what's the out. Okay, let me show you. Yeah. So starting from here, we do convolutions, and let me one convolutions, and the first block. So I guess the first block means this. So we have two consecutive convolutions with skip connections. That's why we have. Now I don't think I need to explain it. So this is how we implement it in the skip connections in Keras. So now second block and third block is pretty much the same. You have comp, and we have skip connections. And the skip connections now we are right here. Now this is now we need to do upsampling. So that's why we can expect it. We can see comp to the transpose. That's the first time. So I guess we are here and do convolutions, and these the outputs. That's the kind of basic structures that I want to use in these lectures. Again, this one is not the optimized one. I don't care about whether this is good, this structure is good or not. I'm just want to show that how to implement it. So the structures, you guys can try different size or different number of layers, whatever. Okay, now we have to define what kind of optimizer that we're going to use, and what kind of loss, the definitions and the metrics, things like that. Here we use mean absolute errors. So I'm about to show you. Let me see. So this one is now we're done with the training, and hoping that these structures trying to learn the prior knowledge from data set. That's basically what we are doing. Basically, if we would do in one-dimensional space, suppose we have two data points, and what kind of prior knowledge in between this is basically we learn it from the data. Prior knowledge. So that's the low resolution image. You feed it into the networks as an input, and that's super resolutions, the output. What do you think? I'm showing different. Okay, so here, let me see. So that's the, we call it super resolutions. I explained the concept of super resolutions using images, but in general, what's the meaning of super resolution is that if you have sparse data set, how can you fill up the blank? That's basically what super resolution does. Right? And suppose you have some data set that you have, and you find out a lot of data missing. Right? If some of the data set is missing, or one or two elements that you are not able to use the data set, and suppose you have small number of data set, so you want to make use of that, the missing data as well, then you have to fill out. Probably you can think of the super resolution as well. How can we fill out the blank? Now let's extremely similar and pretty much I would say it's almost the identical. The previous one is that we have low resolution image, and in this case, suppose somehow the image that we have is blurred. Why? Probably when you take the photos, probably you shake your hands, whatever, or the length of focus is not well adjusted. There are many reasons that. Okay. And I want to do something. What if you have blurred image? How you make sharp, or I will say de-blurred image? I want to do image reconstructions or image restorations like that. Okay. And we have to know the prior knowledge from the blurred to de-blurred. Again, here I want to show you the data-driven approach. So the question that I have is how? How can we prepare the data set that we have in order to teach the FCN networks? Remember the original data set that we have. Starting from high resolutions, we apply the image processing, or we apply downsamplings to get low resolutions. We can do. In the physical world, I mean, suppose that's like have some material images here. Like you take a picture of it, and one is like clean original data set, and in order to have blurred image, probably you can change the focal length, whatever. So thing is that you have synced or paired image. One is blurred and the other one is de-blurred. But the issue is that it's almost extremely difficult or almost impossible in the real world in order to get in the pixel wise, in order to get the exact locations matched. So any ideas? So what we can do is that we get high resolution images, and that's something we can do. And from that one, we do convolutions. What kind of convolutions? Maybe say it's Gaussian filters, whatever, in order to make blurred images. Again, it's apply another imaging processing technique. That's much better. Right? That's how we prepare the data set. Don't even think about to get the blurred image from your experiment. It's not easy. I mean, we can get it, but the issue is that how do you make these two pictures blurred and the original image or high resolutions in order to make these two exactly synced or matched? That's kind of difficult task. So going back to here, to get high resolution or original image and apply the blurring image processing corners or convolutions or filters, whatever, now we can get blurred images. Now move back to another FCM models to build. You can see like it's blurred and deblurred. That's the data set that we prepared, right? Input and output. But in the real world, the output was the input, and the input was the output. You see what I'm talking, right? And another thing that you have to see is that here this one is not super resolutions, so the size of the images are the same, input and output. So as you can see, there's no upsampling part. So I keep the size the same. Probably we can do like kind of auto encoder structures. That's okay, right? You can try that structure as well, but in this case, for the demonstration that I have, is that I didn't change the size of the images or corners. I mean layers in the middle. And as you can see, we have skip connections as well, just like what I demonstrated before, in the case of super resolution. And that's the size of the original image, and convolutions and convolutions and convolutions and skip connections. And we are here, I guess, convolutions and convolutions and skip connections. Now here, convolutions, skip connect. Second and third, yeah, here. Now we have at the final, we have another convolutions, and that's the model that we have. And again, the optimizers and the loss functions are pretty much the same. Now I want to show you the outputs. So we take the blurred image as input for propagations to trained or learned FCM models, and that's the output which is deblurred images. Before deep learning models, kind of super resolutions and deblurrings and denoising, that's not an easy task. Those things are not easy tasks. But as you can see here, if you have the data prepared, nowadays we kind of treat or consider these things are not a difficult task. Okay. Good. Any questions before I move on to another topic? So basically, starting from convolutional autoencoder FCN, like super resolutions and segmentations and the super resolutions and deblurrings are basically we will utilize the FCN structures. So those things are just the example of FCN. And we say image to image translation, example of image to image translations.